All right, welcome back to the drive-through for a fresh, special clean start edition, spell checked by Shiva, 11.3 velocity and acceleration. Hungry? Stop by the deli. Get yourself some Donatos, provided to you by Mr. Kineski today. All right, so the first slide here, this is just all notation, okay? Let's say we've got some function r of t. Okay, now this could be written as f of ti plus g of tj plus h of tk, or it could be written as f of t, g of t, h of t. Okay? The velocity function will be defined as the derivative of the position function. Okay? So we can write that as f prime of t, comma, g prime of t, comma, h prime of t. Okay, the acceleration is the second derivative of the position function, or you can write it as the derivative of the velocity function. Okay? And instead of writing that in vector form, I'll write it like this. So that would be f double prime of t I plus f double prime of, g double prime of t j plus h double prime of tk. Okay, you could also write that, for instance, as v prime of t, comma, no, hold on, nope, sorry, f double prime of t, g double prime of t, h double prime of t. Okay, so to get the acceleration vector valued function, we take the derivative of the velocity's vector valued function. So the speed is the magnitude of the velocity. Speed is not a vector valued function. It's the magnitude of the velocity, which is the magnitude of the derivative of the position function. And so this is the square root of f prime of t squared plus g prime of t squared plus h prime of t squared. Okay? So you're going to see that notation a bunch. All right, let's get started. Given the position function given by r of t equals 2 times the sine of t over 2i plus 2 times the cosine of t over 2j. Find the velocity vector, the speed, and the acceleration vector of a particle moving along this position function. So, one thing I want you to understand is that this is a circle centered at the origin, okay, with a radius of 2. Hopefully you understand that. Even though t over 2 is our variable, that doesn't change the shape of our graph. It only changes when or where positions fall on that curve under various times. And I've placed the orientation on there. Okay, so r prime of t, that's going to be equal to our velocity vector, and the derivative of 2 sine of t over 2, I'll write it now, we'll keep it, I'll write it in that form. Let's see, the derivative of sine is cosine, so it's going to be 1/2 times 2, so that's going to be 1. So it's going to be cosine of t over 2i, and then the derivative of cosine is minus sine, so 1/2 times 2 is 1, so minus sine of t over 2 times j. Okay, now while we're here, let's find the speed. Okay, well, the speed is going to be the magnitude of the velocity function. So that's going to be the square root of cosine of t over 2 squared plus sine of t over 2 squared, because we're squaring a negative, and that's going to equal 1. So our speed is constant. It's always 1. Are you filming me, Misha? Good. Okay. All right. So our speed is constant. I want you to remember that for something we're going to talk about a little bit later. All right. Now, our acceleration vector is the derivative of our velocity function. So the derivative of cosine is negative sine, so that's going to be negative 1/2 sine of t over 2I, and then the derivative of sine is positive, so that's going to be a negative because it's already negative. 1/2 cosine of t over 2j. So what I want you to notice is that the acceleration vector is not 0, but our speed is constant. Our acceleration is not 0, but our speed is constant. How can that happen? It happens a lot this way in physics. But this is what's kind of nice about breaking them up into vectors, is we can just put something in and see what happens. So let t equal pi. All right. At t equals pi, our position function, r of t, would be what? 2 times the sine of pi over 2. Sine of pi over 2 is 1, so that's going to be 2i. 2 times the cosine of pi over 2. Cosine of pi over 2 is 0, right? Right? That's good. That's good. That's what we got. I hate it when this happens. Look, they got sine as their I and cosine as their j, and that throws me off because it's not what we're used to seeing. Okay? So that would be right. R of t would be 2 comma 0. So at pi, we get this vector. That's just our position vector. It points it to right there. I'm going to erase that because it's going to end up confusing us next time. All right. Our velocity vector, so v of pi, sorry, this should say r of pi. R of pi. V of pi, well, that's going to be cosine of pi over 2, which is 0, comma, negative sine, so that's kind of a negative 2. So at this point, our velocity is this way. Okay, now let's look at our acceleration. Our acceleration would be negative 1/2 times the sine of pi over 2. Sine of pi over 2 is 1, so it's going to be negative 1/2, comma, 0. All right, let's go back. I got this all wrong. All right, let's clean this up. I apologize. At pi, the velocity is this. I'll see you guys tomorrow. That is our velocity. Okay? Our acceleration is this. Notice that those two are orthogonal. That's going to be the case at all points on this circle, and that explains how the speed is constant, but the acceleration is not the 0 vector. All of our acceleration is pointed towards the center of the circle, okay, where our velocity or our speed is running tangent to the circle, and that's what allows our speed to be constant. Okay, let's do a couple more. So, an object starts from rest. So what that tells you is that our initial velocity is 0, okay? At the point at the point 1, 2, 0. So, our initial position is 1, 2, 0, and moves with an acceleration of, okay, so now we know a of t is equal to 0, 1, 2, where acceleration is measured in feet per second per second. Find the location, so we need to find r of t of the object when t equals 2 seconds. So, we need to find rt. We've written down what we know. So, if that's a of t, the integral of a of t is going to give us v of t. Okay? So, v of t is going to be the integral of 0 plus dt plus the integral of 1 plus the integral of 2. Okay? So, that is C1. The integral of 0 is just a constant. It's 0 plus a constant. The integral of 1 is t plus some other constant. And the integral of 2 is 2t plus some constant. So this right here is our v of t. However, we know that our v of 0 is 0, and therefore C1, C2, and C3 must all be 0, because if we put in a 0 for our t, we're going to get the 0 vector because we are starting from rest. So then we know that v of t is equal to 0, t, 2t. And now we have our definite velocity function. Now we want our position function. So let's integrate. I'll just switch colors here. Let's integrate our velocity function to give ourselves our position function. Well, r of t, the integral of 0 is still 0 plus, we'll call it c4. So it's 0 plus c4, comma, the integral of t is t squared over 2 plus c5, and the integral of 2t is 2t squared over 2. So that's just t squared plus c6. But we have some information. R of 0 is 1, 2, 0. So that means C4 is 1. Can you see that? C5, oh, come on. C5, let's see, put in a 0. You're going to get a 2, so C5 is 2. And C6 is 0. So our definite R of t function is 1, 0 plus 1, comma, t squared over 2 plus 2, comma, t squared. Okay? So if we want to find the location of the object when t equals 2, we will write that as r of 2, and that's going to be, well, it'll be a vector, but it wants the location, so we'll just write it as a point, okay? And that's going to be the endpoint of the vector 1, comma 2, comma 4, and that is the location of our vector valued function at r equals 2, or sorry, at t equals 2. All right, one more. So this will kind of be like the example that you guys are going to provide for me. Suppose that you hurl a wedge of Gouda cheese from the corner of a roof of a building 50 feet above the ground. So you're on this pink building. Okay? This Gouda here is 50 feet above the ground. And you launch the cheese with an initial velocity, so you got some vector represented by 8, 6, 4. Alright, so we know our initial position is 0, 0, 50. We know that our initial velocity is 8, 6, 4. Okay, now your roommate standing on the ground is somewhere over here. So here's our X, here's our Y, somewhere over here is your roommate. We'll get to him and her in a minute. Okay? Will your cheese hit your roommate? So what we're going to need to do is find our R of t again. And it seems like we're not given very much information at all. Okay, so we're trying to find our R of t. Here's what we know that's stated without being stated. Our initial, or sorry, not our initial, the acceleration vector we know. The only acceleration on this block of Gouda is gravity. And since we're in feet, that acceleration vector will be written like that. So we will go with 9.8 meters per second squared and 32 feet per second squared. Alright, so look, if we want to integrate A of t, that would give us V of t. Now I'm just changing the way I write this a little bit. Hopefully you watched the chapter 11.2 video pretty well. Now I'm just referring to all these constants as a constant vector. Okay, well, we know that our initial velocity is 8, 6, 4. So that means our C must be 8, 6, 4. That's our C1, C2, and C3 all wrapped into one. So that makes V of t equal to 8, 6, negative 32t plus 4. Okay? Now, we want to find our R of t. So we're going to have to integrate our V of t to get our R of t. Well, that's going to be 8t, 6t, negative 32t squared over 2, so negative 16t squared plus 4t. Hopefully you followed all that. It's just integration. Okay, but again, that's a plus c. And our initial conditions, R of 0 was 0, 0, 50. Okay, you can consider that a position or a vector, because remember that these are vector value functions and we're tracing out the endpoint of the vector. So that makes our C is 0, 0, 50. So our actual R of t is 8t, 6t, 50 plus 4t minus 16t squared. Okay? Well, we want to know, is this block of Gouda going to hit our roommate? Well, one thing that I know about my roommate that you don't know is that our roommate is 6 feet tall. And so, in order for us to find this, we need to isolate one of these components. So, let's figure out when will our z value be 6 feet. 16t squared, sorry. Okay, and you end up getting 0 is 44 plus 4t minus 16t squared, or 4t squared minus t minus 11 is equal to 0. When you pop that in to the quadratic formula, you get, the only thing that we care about is t equals our positive version. The negative answer for t is going to be, let me scroll up and explain this to you. Alright, so you're tossing this, it's going to be a parabolic path, okay? Somewhere here in the future, t equals positive. We want to see if it's going to hit them in the face. Well, the negative answer would be where it would have gone if you could back up time, which you cannot in this problem because you can't, you know, create a time machine and reverse your Gouda path and have this person be in the building. All right, so you end up with a quadratic formula getting t equals 1.788 seconds. And when you pop that into r of t, you get r of 1.788, and you end up, not coincidentally, getting 14.3 feet, comma, 10.73 feet, comma, 6. And if you look at 14.3 feet by 10.73 feet, oh boy, you're going to hit your roommate right on top of the head. Boom!